Alright, so last time we talked about linear momentum equations as far as when your velocity profile has a geometry wherein those coordinates actually influence the integral. Here we're actually just going to talk about what do you do when you're having multiple dimensions in your linear momentum equation. So here we're going to be doing 2D linear momentum equations, three-dimensional linear momentum equations, which we'll usually just reduce to 2 dimensions, and we'll see how that really affects the integrals that you do as far as the control volumes and the control surfaces. So here we have a problem with a pipe, and unlike the pipes before, which were just circular and all the forces were collinear, which means you can make really simple vector equations, here we have the pipe twisting and then flow coming out of this outlet at this angle. So let's start with our basic transport equations. So like I was saying before, just Reynolds transport theorem for linear momentum. So since you've already seen this in the past 2 videos, I'm just going to put it in this form. So as you remember, on the left-hand side we have the external forces of the system, internal, external pressures, and here we have a control volume term and a control surface term. Once again, we should figure out what assumptions we want to use for this problem. We're going to use the assumptions that we usually use, and that's that the flow is incompressible. Again, that means that rho is constant, the density. We're going to assume that the flow is steady state, which means that time derivatives go to 0. And the assumption we'll add, since we talked about it so much last time, is that velocity profile is constant. And what that means is that the velocity at whatever control surface you're looking at does not depend on geometry of that cross section. So if you have a circular pipe and your fluid is moving through that circular pipe, the cross sections will have circular geometry at the inlet and the outlet. But if we're assuming there's no sort of laminar flow or turbulent flow, we're just assuming that the velocity profile is constant at that point, then velocity does not depend on radius, and we don't have to worry about that inside our integrals. The reason I'm making that assumption here is that there is no flow regime at any of these indicated. They're just saying the flow is going in at the inlet and the flow is going out at the outlet. So we're not going to worry about parabolic flows within the system. Okay, so the next thing we should do is identify the control volume, which is pretty simple in this case because we're looking at one small segment of pipe, and our control surfaces. Again, pretty simple because we're just basically giving them in the problem. So right here and right here, those are our control surfaces. Okay, now let's take a look at our linear momentum equation. So as I said before, we're assuming that everything is steady state, so this control volume term is once again going to go to 0. Okay, now that we have that done, we could start enumerating the forces we have on the system. So what are the external forces that we have? Okay, so if you've read the problem statement, we're basically at the end of the day looking for the reaction forces that are happening at this flange bolt here. So this bolt is basically adjusted to whatever flow is going through the system, and it's designed so that the system stays static. So it keeps everything from falling apart. We don't know the direction of these internal forces, and we don't know the magnitude, but typically, again, when we have these sorts of forces, we just assume that they are going to be positive. Point I'm going to make is that right now we should assume that everything is positive, and since we're doing a multi-dimensional problem, the vectors will actually tell us the signs later. So we're going to keep things as simple as possible. We're just going to say there's a pressure at the inlet, there's a pressure at the outlet, there's some sort of reaction force happening at one, and because we have an inlet and outlet, and those are both our control surfaces, we're going to have 2 integrals from the control surfaces. So I'll put that equation up here. Again, remember last time we called one of these negative. We called the outward pressure negative, but that's because we had a pipe that was just all along from left to right, and the pressure points inward at every point, so in that case it was going left. Here, if you look at the pressure, it's going to be pointing inward along this vector here, so it's actually going to be positive in the right direction and positive in the upward direction. But at this point in time, we've just written the vector equation. We haven't worried about any of the negative signs. That will come up later. So typically there's two ways of solving these sorts of multi-dimensional linear momentum equations. One of them is you go through the system and you basically break each force that you see into components along each dimension. So over here you break this, I guess, flow into an x-ward direction and a y-ward direction. Same thing for the reaction force, and same thing at the inlet. I would actually recommend just writing all the vector equations and just working with the vectors instead, and worrying about decomposing that into two different equations later on. So in that case, what I recommend is once you've written your overall linear momentum equation, you should list the vector for each of the vectors that are in the equation. So P in, P out, this reaction force vector, V in, V out, and both the normal vectors. So you could do that basically just by looking at the picture. And you need to be a little bit careful because you don't actually know a lot of these, but that's fine. You just need to be able to write what they are without actually knowing the magnitudes. So for instance, we know that the inlet pressure over here, since pressure points at every point inward in the system, is going to be going to the right. So when I write this in triangular bracket notation, I'm just going to say the vector of the pressure inward is just going to have the magnitude of that vector completely going to the right. So if I were to pull this out, you'd see that this is just a directional unit vector times whatever magnitude I'm working with. In this case, since it's the pressure vector, I have the pressure's magnitude multiplied by that unit vector. Similarly, you do have a vector you can write for the outlet pressure, and if you were to do that, it would look like this. Again, since it's pointing inward on the system, it's going to be up and right, so both components are going to be positive. But if you remember from the problem, we are working once again with gauge pressure. And even if we weren't given gauge pressure in the problem, I recommend just making all your pressures gauge. Because what that does is that at this outlet, once again, you could just call it 0, and then we don't even have to worry about it later, which greatly simplifies the calculations you're going to have to do later on. So I'm going to cross that out right over here. Okay, nextly, at the dot products over here. So if you've done enough fluid mechanics problems so far, especially in the last examples that we did, usually those dot products simply simplify to either +1 or -1. And if you're using this method, that's pretty much going to be the case as it was before. So at the inlet, the velocity was simply going to the right, so it's going to look the same as the pressure vector. And the normal vector at that point is going to be in opposition, just like usual. That's why you usually get the inlet. The dot product turns out to be simply -1. So I'll show that right here. Okay, what about at the outlet? Well, it's also going to be pretty similar to usual. You're just going to have both of them pointing in the same direction, because the flow is actually going to be going out, and the normal vector is going to be pointing out as well. So what you have is this and this. Okay, I'll scroll up a bit just to explain the signs here. So as the velocity of the water is pointing outward, you'll see that it's going both left and down. So as you see this angle to the horizontal, cosine 40 is going to get you the horizontal component, and sine 40 is going to get you the vertical component. And again, since they're going left and down, it's going to be negative. And like I said before, the normal vector is going to have the exact same trigonometric form as the velocity. And if you think about what that dot product geometrically means, you already know since it points in the same direction, your dot product should be 1. And, sorry, if you do that calculation, of course it's going to turn out to be just that. again, the dot product will, okay, I should misstate that, well, I should state that again a little bit. So the magnitudes will multiply against whatever the angle is, and since the angle is the same, the angle you get will be 1. And of course, since that normal vector has a magnitude of 1, because it's a unit vector, you're just going to simply have the velocity that's being taken with that dot product. So here, for the inlet, you're just going to get the dot product to come out to be negative whatever your velocity is in the inlet. At the outlet, it's going to be positive. So nothing there is different than usual. Okay, so now that we've listed in triangular bracket notation each one of these vectors, what we're going to do is we're going to sub that back into this equation here. And it's going to look a little bit like a mess, but don't get so lost in the math, we're just doing a substitution, so it's not too bad. Okay, so that's going to look like this. So on the left-hand side, again, we just have those forces. We canceled out the outward pressure, so that's that 0 here. We have the inward pressure, and remember that's just pointing directly to the right. And we've decomposed our reaction force into an x component and a y component. This is what we're looking for. We haven't found either of these yet. Okay, and over here, we still haven't computed those integrals yet, but you'll see with the assumptions that we made that the system is, the flow regime is incompressible and the velocity profile is constant. We're actually going to be able to pull everything out of the integral like we usually do and simply integrate over the area, which means we're just going to get the area at those cross sections. So again, this is the negative V in from that dot product, this is the V out from that dot product, and you still need to include the vector that you originally had. So once you've done all that, this is what your equations will look like. Okay. That is to say, once you have this vector equation written, you should decompose it into the two directions that you're working in. So all the x components will go down into this equation here, and all the y components will go into the second equation down here. Remember, the integral is just over the area, so we're just going to get this rho VAV term that we've seen many times in the past. At this point in time, the problem is essentially solved. You know most of these quantities, but what you should do, and what you should always do, is go back to the continuity equation and see if you get what you expect. So here, given our assumptions, flow is incompressible, steady state, velocity profile constant, we're going to see the same thing that we usually see, which means that whatever flow is at the inlet is going to be the same as the flow at the outlet, because that volumetric flow is going to be conserved throughout the system. So you're going to see V in times A in equals the volumetric flow rate, and that's going to equal V out times A out. So at this point, all you need to do is take this flow rate that we were initially given and find the velocities from the areas. Again, the reason we write everything in the form rho VAV is because this AV is your Q, and this rho times Q is really your m dot. I've mentioned this before. So you're already given Q at the beginning of the problem, so both of these you could just, they're the same. So you can just put the Q here, but you need to find the V. And the V you're simply going to get from taking that Q and dividing it by the area. And the area you're just going to know is going to be the same area of a circle that you've been using in the previous problem. So pi, whatever the D is there, squared over 4. Okay. So hopefully that made some sense. Again, the procedure we went through is just our normal one. Create the linear momentum equation, write it out in vector form, find each of the vectors, compute the dot products, then you'll get your linear momentum equation vectorized. You should do the integrals and then break the overall linear momentum equation into each dimension. So in this case along the x and then along the y. Let's look at another pretty similar example. In this problem you have flow coming out from the nozzle and it's hitting some sort of board and splitting into two different streams. And we're being told that the flow from the beginning, Q is being split into alpha Q and 1 minus alpha Q. So right off the bat, you'll know that just as in the previous problem, what that's implying is that your continuity equation will look like this. Q equals, I'm just going to call it AQ plus 1 minus AQ. So it's exactly what you were seeing before. The flow at the inlet is the same as the flow at the outlets, summed. So if you add these together, you're just going to get Q equals Q, or 1 equals 1. So the assumptions are going to be the same assumptions as last time. It's going to be that, again, the flow is incompressible, velocity profile is constant, and we're working again under steady state. Okay. So the other thing that this problem is asking for is it's asking for us to find alpha. And in doing these sorts of two-dimensional linear momentum problems, the perhaps most important thing you could do is think about the geometry you're working in and choosing the simplest geometry you can possibly do to solve the problem. Since we're interested about this alpha, the smartest thing to do is going to be, just like those incline problems that you've done in general physics, is rotate the plane so that we greatly simplify the vector geometry before we do the problem. So I'm going to be working with this picture over here. So we've simply rotated this entire thing over by theta, and we have this now. Okay, then we just do what we usually do. We're going to first write the linear momentum equation, same way we have before. I'm going to skip a few steps. Okay, it's going to look like this. Let me explain. So, just as before, our control volume is going to be this entire system, like so, and we're going to have 3 control surfaces, one here at this outlet, one here at this outlet, and one here at this inlet. They actually already labeled them for us, so we have this control surface, and this control surface. Remember, we already assumed that the problem was going to be steady state, so we don't have to worry about any control volume terms over here. Similarly, on the left, they're telling us not to worry about the pressures here. They haven't put any P's on the picture over here, so the only forces we have to worry about are this normal force that they've indicated to us and this tangential force, which I've only added in for sake of notation. They've already told us that it's 0, so you can simply cross it off at the beginning, just like this. Okay, so just like we did last time, what we should do is we should identify vectors for each of these, well, vectors that we're given. So the reason why we did this again is that these two outlet vectors are going to be simple to write. So V2, which is just going to right, is just going to be 1, 0 times whatever magnitude it is. We don't know what that is yet. V3 is just going to the left, so it's going to be negative 1, 0 times the magnitude again that we don't know. And just as usual for the outlets, the normal vector is going to be in the same form as the directional vector for the velocity. So when you do the dot product, you're simply going to get V2 and V3, because the angle turns out to be 1. A little bit more complicated, but not too complicated, is that inlet velocity, simply because we rotated everything. So if you see this angle over here, you should be able to see that this angle at this point is going to be the same thing. It's going to be theta, which means that we could simply use the trigonometry at this point to generate whatever our projections are going to be at this point. So if this is going down and right, cosine theta will be the horizontal component once again, and sine theta will be the vertical component. So that looks like this. Okay. So yeah, this is should be v1 sine theta. So put that in here, v1 sine theta. Again, it doesn't really matter too much, since we're not really interested in finding the force. If we were interested in finding this normal force, this would be more important. So if you do this dot product, what you're going to get is what you usually get, and that's going to be negative times whatever magnitude the velocity had. So it's just going to be negative v1. I think this angle over here should also be negative. No, it's actually going to be pointing, because it's the inlet, it's going to be pointing up and left, so the x component will be negative and the y component will be positive. So this is right. Okay, cool. Over here the velocity is pointing right and down, so this will be positive and this should be negative. Okay. The other thing, okay, so actually we've noted all our vectors, so let's put those vectors back into the linear momentum equation. So again, over here you have that tangential force, which is just going to be 0, 0, because we're told it doesn't have any magnitude. And here is what our expression looks like after these integrals. So again, since we've assumed that the velocity profile is constant at these points, it means that the velocity does not depend on the geometry of the cross-section, which means that v comes out, rho comes out, the dot product comes out, and you're just integrating over the area of dA, which just gets you dA. Well, it gets you A at the inlet and the outlet. So that's going to look like this. Okay. At this point, I'm going to bring up again the reason we really care about writing things in the form of rho VAV, and that's because over here you see this VA, over here you see this VA, and over here you see this VA. So each of these will actually come out to be just Q. So this will be Q, this will be Q, and this will be Q. Okay, and the other thing we should do is we should split this into components. So we'll make an equation for the x components and an equation for the y components. And that will look something like this. If we're interested in alpha, we'll just look at the horizontal. Let me make a note of that over here. This is horizontal. And that looks like this. With those vectors, we could drop the vector notation since everything is collinear at this point. We could just do a regular scalar balance. And over here, as I was saying before, we could replace each of those with Q's, so that's going to look like this. I should be a little bit more careful. Not exactly Q, it's going to be in the form that we have of the continuity equation up here. So the inlet is going to have this flow, and each of the outlet points will have these, alpha Q and 1 minus alpha Q, as they're written over here. But what I meant to say was that everything is going to be the form of something times Q, so these Q's are all going to cancel out. So this won't matter because there's a 0 over here, this won't matter, and this won't matter. Same thing with the rows, all the rows will just simply cancel out, because we could divide through by them and they're not 0. The last part of this problem is just, once you've already done the hard parts, just do the remaining algebra. And remember that V1 equals V2 equals V3, that was just something that was given in the problem. So this original picture just has a V here, a V here, and a V here, so they're all the same. It's stated again over here that V equals V jet. When they split, they have the same velocity. So that just simply gets you this result down here. And then you do a little bit of algebra, and you find out the final alpha, and that's just going to be this. Again, we could go back and solve the normal, or the y equation for the force, but again, we're not given any numbers, so we just get an expression for that. So nothing too illuminating from doing that. Alright, let's look at one more problem. So this one's a little bit trickier. So basically you have a stream coming in through the inlet here, and then it's basically hitting a conal part at the end, or conical part at the end, and coming out in a bunch of different directions. A spray, up and down over here. But again, you have to be careful because the way we're looking at this is we're just looking at cross-section. The actual geometry, if you're going to imagine it, would look something like this, where you have the flow coming in in here the side, but in here the top, and spreading out through the bottom in a radial direction. And this continues not only as a semicircle, but around the back, so everything basically goes out radially. So you need to be a little bit careful about how you represent the geometry when you're going to set up your equation. And if we're looking at control surfaces, notice that your control surface at the inlet is going to be circular, but your control surface at the outlet is not going to be circular. It's actually going to be a shell. So whatever your diameter is at this point, you're going to be working with an area of 2 pi r, and then what they're calling t is thickness. So it's actually going to be a circumference times some sort of thickness, so that'll get you your shell of area for your cross section or whatever's coming out of the outlet. Alright, so let's do what we usually do. This is the control volume. These points are the control surfaces. This inlet here, this outlet here, this outlet here. Okay, next step is write the linear momentum equation. Again, that looks like this. Just the external forces on the left, and the surface integrals on the right. Because again, I'll say it again, what are our assumptions? Flow is incompressible, steady state, and velocity profile is constant. That means again is that after we've done these dot products, we could simply pull rho and v outside the integral and just integrate over dA. First, let's think a little bit about the vectors once again. So this force, well, they've already helped us a bunch by giving us the geometry in this picture. This force is simply going to point in the x direction. If you're working in cylindrical, you might think of this as the z direction, but it's just a difference in notation. And the flows over here are going to be pointing in what they're calling the r hat direction, or the unit vector corresponding to r. So this gets a little bit confusing because if you're thinking in true cylindrical coordinates, the r vector will actually point out along all these points. So it should be positive at both the top and the bottom if you're looking at it in this geometry over here on the right. But because we're just looking at this cross section over here, you have to call one of these the positive direction and one of these the negative direction, even though in true cylindrical coordinates they're both going to be positive. The reason we need to do this is when we're writing our linear momentum equation with this cross-sectional geometry over here, you need some sort of way to say that the symmetry cancels out the forces. So in other words, when you write a force equation for the radial direction and everything's spraying out radially, you know that this vector over here of the fluid coming out at this point is going to be completely equal to whatever is pointing out over here. Similarly, if you have something like this, on the other side of the plate there will be another vector pointing out like this that's going to cancel it out. So your momentum equation in the radial direction will actually come out to 0 because all the flows coming out in the radial direction will have a symmetric partner on the other side of the circle. So that's a little hard to realize, but they've already given you the geometry of the picture, so you just need to make one of these positive and one of these negative in the radial direction. So again, this force pointing left. The dot product here, because it was an inlet, is evaluated to negative V in. and over here evaluates to positive V out. And like I said a second ago, because of the geometry in the picture, we need to account for that by having this. So again, one of the flows goes up, one of the flows goes down. So one of them needs to be positive, one of them needs to be negative. And as you can see, these two terms over here will cancel out completely, leaving you just this. And this has already been decomposed into just along the x direction. So we could drop this vector notation here, and you're going to get something that looks like this. And the V in they're talking about in the problem, they're calling U, so I changed that here. This V in simply goes to U squared. Negative signs are on both sides, so they cancel out. And our area at the inlet is simply that circle here, so pi d squared over 4. So that's one of the things they asked us to find was the force. The other thing they want us to find is the thickness of the shell that's coming outward. And as I said before, the momentum equation can't do anything because you have all the momentum in the radial direction canceling out because of those symmetry partners across the circle. But if we look at mass conservation, if we look back at the continuity equation, given our assumptions already, we know that volumetric flow is going to be the same throughout. So V in A in equals V out, A out. And this time, we're going to look at the geometry in 3D. So we're going to go back to this picture. We're going to say, okay, that has to be 2 pi r times thickness. And that gets us this. So the inlet we already found, that was this before, and the outlet is 2 pi d over 2 times the thickness. And again, from the problem, we're told that, like last time, the velocity out is going to be the same thing as the velocity in. So we could simply make those cancellations here. So V in cancels with V out, pi cancels out with pi, and you're left with the thickness equals the little diameter squared of the inlet divided by 4 times the larger diameter at this spraying point over here. Alright, that's about it for now. Next time we'll do unsteady state flow.